This is the screencast of section 6.2, example 4, substitution in indefinite integrals. So here's the point where we start taking antiderivatives of things that we just can't see right away. We've got to do a little work to do an antiderivative. Not that you haven't had to do work before, because believe me, you have. Antidifferentiation using substitution is used when the inside piece of a composition function is related to an outside piece by a derivative. So in example 4 here, first of all, we have a composition function, e to the u. Cosine of x is inside e to the u. So there's your composition function. Now cosine of x and an outside piece, sine of x, are related by a derivative. So u substitution might work. That would be my first thing I would go to. So let's start out by defining u as the inside function in a composition. So off to the side here, I'm going to call u cosine of x. Now, part of earning points on an AP exam for u substitution is defining what u is. You can't just throw down the letter u and not define what it is. Now, also, we are going to take the derivative of u. So du dx equals the derivative of cosine, which is negative sine of x. Now we want to solve for dx. dx is in our function. We want to solve for that so we can substitute in an expression. So that means du over negative sine of x is dx. Now I've got some substitution to do. I'm going to take the antiderivative of sine of x times e to the cosine of x got called u, so I'm going to plug that u in, I'm going to substitute that in. Then dx is du over negative sine of x. So now I've got u's and x's all over the place, dx went away, I've got a du. Well, let's simplify. See what happens here. This sine of x is technically in the numerator, that sine of x is in the denominator, so now I can put the negative on the outside, and I'm taking the antiderivative of e to the u and now just du, which is an antiderivative we can take. So now I'm going to do negative antiderivative of e to the u is e to the u, of course, plus c, but u wasn't the original problem. In the original problem, we created that. So we need to put back in what u stood for, and that was cosine of x. So that's negative e to the cosine of x plus c. Now, a good practice to get into with u substitution is verifying. So off to the side now, I'm going to verify, like we learned in the last example, by taking the derivative with respect to x of negative e to the cosine x plus c. Alright, so the derivative of negative e to the cosine of x, so that's still negative, and that's e to the u. So I have e to the u times the derivative of u, so that's negative sine of x, and then the derivative of c is 0. So now the two negatives cancel out, and I get sine of x e to the cosine x. So I did verify that, in fact, what I found for my antiderivative, if I take its derivative, I get the inside function that I was antideriving or integrating in the first place. Then I'll try problem number 19. It cheats for you. It tells you what u should be. I don't like it. Do not assume that this is going to happen. It will not happen on an AP exam or your test. Use the indicated substitution to evaluate the integral. Confirm your answer by differentiation. So we are going to verify again. Alright, so number 19. Secant 2x, tangent 2x, dx. Alright, so now this is a composition function, but it's got two parts, secant and tangent. So I have to separate the 2x, which is the inside part of the composition function, that's how they get u equals 2x, and then the outside secant tangent. I can take the antiderivative of secant tangent. Now remember I said you use this when your u is related to something outside by a derivative. Well, what's the derivative of u? That's just 2. So a constant doesn't have to cancel out with anything, so it shouldn't be a problem with u substitution. So let's start. I'm going to rewrite u equals 2x, and I'm going to take the derivative and solve for dx. And now I'm going to substitute in those parts. So I have the antiderivative of secant of not 2x anymore, but we're calling that u, tangent of not 2x, but we're also calling that u. And then instead of dx, I'm going to substitute in du over 2. So now my 1/2 can come out as the coefficient. Remember, that's what I said, it can just escape. The coefficients don't matter. It's like if we had an extra x in here, that would have to cancel out. So now I'm taking the antiderivative of secant u tangent u with the du afterwards, and of course the antiderivative of secant u tangent u is just secant u, and then I have a plus c. I can't leave u in the problem because that's something I created. I have to put back in what u stood for, and that's 2x, so 1/2 secant of 2x plus c. So let's verify. I'm going to take the derivative of my answer and see if it ends up to be my integrand. Alright, so the derivative of 1/2 secant of 2x, well, the 1/2 stays there, but the derivative of secant is secant, the derivative of secant u is secant u tangent u times the derivative of u, so the derivative of 2x is just 2, and then plus the derivative of c, which is 0. My 2 and 1/2 will cancel out, so I end up with secant of 2x tangent of 2x, which is in fact my integrand.